All right, so I hope everybody's doing well. Today we are going to be doing our first lab on simulations, and actually our only lab on simulations. So I'm just going to load up Solidworks real fast. You'll notice that today I am working from VLabs just like you guys. My goal in doing this is actually make sure that things are a little more standard this time. I know there was some confusion during the last assembly lab. So today what we're going to be doing is we're going to be doing a physics simulation of multiple parts, and to do that, we're going to be doing it in an assembly. So I'm just going to click on my assembly option and let that load up. Now, quick things about assemblies, because we didn't get too far into this in the last class, and I think it's kind of helpful to get into it now. The first part you put in an assembly is your ground part. It's fixed to the plane and it can't be moved anywhere. I mentioned this, but I'm not entirely clear on how many people realize this. So let me just go grab the files from this week. So the first file we want to put in is the file that we want to be locked in place. So today we're going to be doing a crankshaft rather than the CNC blocks we've done before. And the reason for that is that when we wanted to go and do the simulation blocks, we realized that it's really useful to have something that's kind of visually appealing and kind of easy to see what's going on. Whereas on the CNC blocks, it's a lot of enclosed parts and a lot of threaded rods moving, so it's not quite as engaging. So today we're going to start out with this system. So I'm going to start out with my lowercase and just drop it into place. There we go. So this is the lowercase of the camshaft. It is cut in half, so normally this would be two pieces, but we have it in one piece, so that way you guys can just see inside the system as it's running. So this piece cannot be moved. It is fixed. If I right-click on, or left-click on it, excuse me, you can see that it will give me the option to float it, which is how you can tell something is fixed. You can also come down here and take a look at the fact that it says fully defined. So we know this part can't go anywhere. This is a great place to start out with. So the next thing I'm going to do is I'm going to insert another component. And I'm going to go a little bit faster this time, just because this is something we've done before. So I'm going to grab the uppercase, drop it in place. And then the uppercase is actually, it is the same, both top and bottom. It is symmetric, so we don't need to worry too much about it. So I'm going to choose the bottom of the uppercase and the top of the lowercase. I'm going to mate these two faces together and flip them, so they're in the right direction. And then they are, luckily for us, exactly the same width, so we can just hit that button and everything lines up nice and neat. So that is how that is assembled. I know that that's got a sharp edge, but I was not feeling particularly good as a designer this week, so you can feel free to give me some flack for that later. So that's in place. This is fully defined. It's nice and solid. This is the case for the engine that we're building today. So I'm going to hit mate. And excuse me, I'm going to hit insert components, and I'm going to add in the next component that we want to work with. And so in this case, this is going to be the crankshaft. And the crankshaft actually controls the crank directly. And so we're going to come in. I'm going to mate my crankshaft circles. I'm going to make my crankshaft exteriors. And if you've done everything properly, it should just spin in place right now. You'll notice it now says underdefined, but that's okay because it is where it needs to be. The next thing we do need to do is we need to use the actual crank itself, the crank rod. So I'm going to drop that in place. And this is a tricky mate to do, and there's two reasons for that. First and foremost is that if I try and make this a coincident mate on something, and I'm just going to actually do that so you guys can see it. Do not do this if you were following along until I tell you to jump back in. I'm going to make this a concentric, and then I could hypothetically just go up to this wall, but the problem now is that the shaft that I'm working on is not centered. And you can see that it's really off onto the edge. And so while this system does work and it'll turn and it'll do all the things I want it to do, this just isn't right because that's not in where it's supposed to be. So I'm going to actually undo everything I just did. It's going to get a little mad at me. There we go. And now if you're following along, this is what we're going to be doing. So I'm going to start with that same concentric mate. That's important to make sure that it stays on the shaft. And that way, as this rotates, it follows along with that. But rather than use these mates or a parallel mate or any of these fancy mates, I'm going to go down to an advanced mate. And in the advanced mate, there's this option for a width mate. And the width mate actually lets me place two objects directly in the center of one another. So what I'll do is I'm going to choose both sides of the crank rod. And then I'm going to choose both interior sides of the crankshaft. And you'll see that right there, it's actually lined it up perfectly down the middle. And this is a really useful mate for whenever you don't want to have to do measuring or you don't want to get too crazy with it. You can just kind of center something and call it a day. There are other mates we could use for this that get into that. So we can have like a cam mat mate or potentially even a hinge mate, which would work in this. But we're just going to stick with that width mate because it's really nice and easy and we can center it and it behaves very, very cleanly. So I'm going to hit OK. And now you can see that our crankshaft is loaded onto our camshaft. So we're in good shape. Everything is sort of coming together. We got one more part to add in here. I'm going to insert components. And I'm going to actually grab the physical shaft itself. This is often just called the piston head. And we are going to, again, do a concentric mate. So this is how those will be mated together. And then I'm going to mate the piston to the piston shaft. There we go. And so now this entire system is actually nice and neat and super clean. I can come through and I can rotate this system, and I can see kind of how this reciprocating engine would work. So hypothetically, if this was a real engine, you would have some sort of explosion that would push down on the piston, and in pushing down on the piston, I would create some sort of mechanical motion down here. For the purposes of today, we're going to be doing everything from the crankshaft. So we're going to pretend this is just like a model of the system. All right. So I could sit here and I could just record my screen as I do this, but this isn't super professional. I want to actually come through and do some physics work on this and kind of get a feel for how it should be behaving. And to do that, I'm going to be doing a motion study. Before I get into that, though, I want to stress two things. First and foremost is, to set that up, you have to go up here to your settings options and go to add-ins. And you'll see here that there's an option for Solidworks motion. So you want to make sure that that is selected and just hit OK. If you're not feeling that, you can also just go to add-ins and make sure that that is highlighted. Sometimes if you're using SolidWorks, especially on your computer, just make sure that that is there right there. And what that's going to do is that when we come down here to motion study, up here on the left, you'll see that this is set up for animation. What animation lets me do is I can actually move my part and then set a new time frame, and then move my part again and set a new time frame, and so on and so forth. And I can actually play it back to myself depending on how that works. I did that badly. But the idea is, I don't know, we can actually go through and do that calculation. But what we want to do is we actually want to be using physics. So we're going to go over to motion analysis. And I'm going to load up a motion analysis option. I'm going to drag it out to 10. So I've got 10 seconds of motion analysis to run. And yeah, so the problem is that while our system is set up, there's really no motion for it to know because it has no forces acting on it. So I want the system to have some forces so I can go from there. So what I'm going to do is I'm going to kind of set up my initial conditions. So I'm just going to kind of set it up like this. And I'm going to use the most basic of forces to work with, which is gravity. So if you'll notice at the top of this plane, there's a ton of different options available for me for creating different forces. So I can add a motor. So I could add a motor, for example, to the shaft. I could add a spring, which, while this model doesn't have a spring option, could be useful for counteracting some force directly. I could add a damper, which is a way of damping two forces. This is oftentimes seen as something like friction, or you could actually be using something like a dashpot, which is reacting directly to the speed of the motion that you're working with. I could add a force directly. So for example, I could put a force directly on the head of this piston to kind of see how it behaves. And I could actually even look at like the contact behavior. So if I've got a set of gears, I could look at how the teeth are meshing. But the one we're going to go with, which is just the easiest one, is we're going to be adding gravity to the study just real fast. And the reason for that is that gravity is a nice, easy thing to work with. And more importantly, it's important to add to most of the studies you're working on because it's going to be acting on pretty much any of your parts no matter what. So I'm going to click on the gravity icon. And you'll see over here on the right that it creates the arrow for gravity. So if we were imagining gravity kind of acting in that direction, not much is going to happen. I want to make sure that it is instead acting downwards. And so in this case, for this model, that's going to be in the Y direction. And if for some reason your model's hooked up differently, you can always play around with this to make sure that it's pointing. Just make sure that your arrow is down, all right, or in the direction of travel that you want to have. And I'm just going to hit OK. And I'm going to, now that I've added gravity to this, I'm just going to hit calculate. And this little calculate button is actually going to go ahead and figure out exactly what this system needs. And you'll see that right now it's just rocking back and forth. And I'm actually going to go back to the beginning and see if it will let me recalculate that. There we go. That's better. That's more fun. So in this case, I just went back to the beginning and I kind of reset my model. And I can do that over and over and over again. I can just drag my timeline all the way back. And I actually want it to be right there. We'll make it real dramatic. And I'm going to hit calculate again. And it'll actually resolve that calculation from that location. So the downside to this model as described is twofold. Mostly, there is no friction. So this is just going to oscillate forever. So no matter what I do, I'm just going to kind of get that constant back and forth. And second, as I'm looking at this, I realize that like it's kind of a really gross animation. It's not a really, really nice and neat. So I'm going to go over my settings real fast, and I'm just going to increase the number of frames to match my monitor. We'll call it 80 instead of 144. I think that's probably unnecessary. And I'm going to rerun this simulation one more time. You'll see it goes a little bit slower. But that is a much neater animation. It's not jumping all over the place. I can kind of get a feel for exactly how it's behaving. And so, okay, we'll wait for this to finish up. And we can do a couple of things here. We can kind of see how this system works just by doing a quick analysis of it as it stands. So let's come on over here. We're going to hit this little XY graph button, and this is going to let us look at our results directly. So I'm going to specifically be looking at the displacement of our model. I'm going to be looking at the linear displacement of the piston itself. And you'll notice that there's a ton of different options here. I can look at acceleration, I can look at velocity. Just linear though, that's what we're doing today. And I'm going to be looking at the magnitude, so the total, the magnitude of displacement for the system, and I'm just going to choose the face of the system for my output. I'm going to hit OK, and it'll actually show me exactly how much linear displacement in inches this has. So it's displacing from 8.1 inches to 9.6 inches, and it's just going up and down and up and down and up and down. And this is in relation to the origin of the part, wherever that is. All right, and this is super helpful, but again, this doesn't look super real. So what I want to do is I want to add a force to this that will actually compensate for that. So I'm going to be adding a damping force, and the reason for that is that damping forces are a pretty good way of approximating some frictions. For this problem in particular, I'm going to be using it just because it behaves a little bit nicer. So I'm going to be adding a torsional damper, like there's the big engine attached to this, and it's kind of adding some resistance, and the damper is going to be attached to right here. And then as I scroll down, you'll see that it gives me how much torsional damping I have. So that's 1 pound per inch, or 1 pound force per inch. That is a lot, like a lot of force. In general, if I was to run the simulation, I doubt it would even move with that. So I'm going to drop this down pretty aggressive. I'm going to drop this down to like 0.001. And you can see how much just adding even just that little bit of damping force changes how this system works. So I'm going to recalculate from the beginning. And you'll see now it is dropping down. And then the damping force is actually stopping the damping force is keeping it from jumping back up. So you can see that it gets down there, it does a little bit of rocking, and then it may stay put. And I can confirm that by going back to my simulation, and I can check my displacement, my linear displacement, my magnitude, and of that face. And you can see it just kind of drops down to 0 and moves from there. All right. So the eagle-eyed among you may have realized that my screen just jumped around a little bit. That's because I crashed VLabs. So make sure to save frequently. I'm glad that I did. But in general, yes, I'm just going to real fast just save this out. Thank you. We're just going to put that on my desktop as... I'm sure I won't ever forget that this is there, just in case, so I don't do that one more time. And we're going to jump back into that motion study now. So taking a look at this motion study directly, you can see that I have a direct displacement for work from, and it kind of behaves the way I would expect, where it kind of drops down and then hangs out there right as is. So this is all well and good, and I can kind of go ahead and play with it a little bit and say, all right, well, what if I want my initial condition to be someplace like here? And I can recalculate, and I can actually see how this system would behave differently depending on how things are going. I can also go over to my system and I can modify what I am seeing with that damper. So I can say, stop. I'm going to edit my feature, and I can change this value around as I see fit. So I could, for example, come in here and just decrease my damping just a little bit more by an order of 10. And I can remodel that and see how we are behaving. So let's just recalculate real fast. And you'll see that that gives me a little more of a what you might expect from a system with really smooth bearings and no load attached to it. And that's actually really the hardest part of simulation, is getting a feel for what is and is not reality. Because sometimes you're going to work on a part and it's going to look completely normal to you, and then you're going to get to the actual real world and you'll find out that no, none of this works as is. But this is the really helpful part of this system, is I can come in here and I can continually check to see how my part is behaving. So I can come back here and say, all right, how did that simulation work? And you'll see that here I've got kind of that structure that we just saw, that kind of bounce and bounce, bounce, bounce. And I can actually play this alongside to see how accurately it matches or where that's happening. And it'll load that alongside. So I can get a feel for kind of where the system's working. So this is all well and good, but it's not super helpful to me, because at the end of the day, I really want to be able to kind of determine how the motor would affect this and what that's going to look like. So I'm going to add a motor to this system, and I'm going to pretend that I'm driving this like it's some sort of, maybe like a prop at the Museum of Science. And so I'm going to click the shaft I want the motor to roll on, and you'll see that it immediately gives me a direction. I can change that direction by clicking this guy over here, but I'm going to leave it clockwise for now because I think that's kind of nice. And I'm actually going to shrink this down just a little bit so we got a little more window room. I'm actually going to run this motor at a constant speed of 100 RPM. And actually, let's make that 10 RPM. That's nice and, excuse me, that's nice and slow and makes things nice and easy. You can go ahead and actually modify this graph so you can change the actual structure that you're working with. So if you've got a specific ramp up or a specific oscillatory behavior, or if you've got like a servo that's driving the system, you can do that too, but we're not going to do that right now. So I'm just going to hit OK. And I'm going to, again, recalculate my model. And what you'll notice here is that in this model, the motor is now constantly driving this system. And so we no longer see the effects of gravity, but we know that they're still there because we haven't removed them. And so now that I've got the motor driving the system and gravity acting on the system, I can actually look at how the system behaves and say, all right, well, obviously displacement is going to be kind of a harmonic structure. So we're going to just double check that. Linear displacement, magnitude, choose the top there. There we go. We'll see we got that nice harmonic and periodic structure. But realistically speaking, the amount of force needed to do that must change based on how gravity is working. So I'm going to real fast. I'm going to do that same system, and I'm going to look at the force in this system instead. And I'm going to say, all right, I want to know what the motor torque requirements are. And I want, again, magnitude. And I'm going to grab, this is going to ask me what I want to grab. I'm actually going to grab the motor from down here. You can't grab it on the page because we don't have a visual representation of the motor. I'm going to hit OK. And you can see that this system is now showing me how this piece works. And I can actually step through this. And I can see that when the piston is higher, I require less force to continue turning the motor than when the piston is lower and pushing it back up. And if you think about it, that means that the piston's energy is actually being handed back to me. So when you guys go run the simulation with your own specific values, you'll see that your torque value will change depending on the damping ratio you've got, the speed that you're running your motor. All of those pieces are going to affect how much torque is needed to move the system. And this is all really cool because with just this very simple tool, I can get a pretty good idea for what kind of dynamic structure I've got without having to leave the simulation workspace. Solidworks can do a lot more than this. You'll see over here that there's the option for doing actual full simulations. So we can actually check and see how a material is deflecting or being affected by a specific action. I am not going to do this in that because it can be computationally intensive to do this, but we can actually see the stresses in this part as it is moving. And we can see where the locations where you're going to see the most stress during operation will be. You can take it a step further, and if you're like me and you like something like automation, you can actually do event-based structures where you can add sensors to this motor and say, hey, rather than try and fire this motor with just a camshaft, I could have some sort of servo motor or some sort of solenoid that's firing my piston, and when it gets to a certain location, I need a fuel injection, and I can add different tasks depending on how that's going. And this is a much more advanced version of Solidworks, but it's really helpful if you're trying to do something like a production line. And you can go even further than that. You can add additional forces, you can add additional dynamics as necessary. And my personal favorite here is actually really the contact option because it lets me see how everything is interacting, whether or not I've got rubbing or if I've got parts that are mashing into one another and causing them to bind up. And I think that's super, super helpful. So for the purposes of today, your goal is just to kind of get this piece together and then make the modifications I ask for you in lab. All you have to do is you just have to run and give me a quick AVI of this as well as the graph outputs. To do that, we're going to do two quick things. To save this file out, I'm going to click the Save Animation button. And this is great because I can literally just save out a quick AVI of what I'm working on. You can use a really high compression quality. I tend to just give it like a 50. That's just me being lazy. It'll run through this animation, and I can actually just go directly to my desktop after this, and I've got a really, really nice animation that I can include in my presentations. So I can just like throw this into a PowerPoint, and I can have this running in the background as I'm describing how the whatever it is that I'm working on works. And you can actually, if I'm being honest with you, I'll normally turn these into GIFs and then put them into my PowerPoints directly because that gives me the ability to actually do a fair amount of presentation without having to worry about where they're coming from. The other thing I can do is, let's say that like I get a result that I'm not expecting. So I'm gonna grab something that you guys don't have. So I'm gonna grab the translational momentum, magnitude of this guy. Hit OK. So there's my translational momentum. Honestly, this is a harmonic behavior, so I'm not super surprised by this, but you'll see that it has a little bit of an expansion arc. It's not a perfectly centered arc. So let's say I want to do some analysis on this. Well, SolidWorks isn't great for that, but I can, right-click on it and hit Export CSV. And this will actually give me an Excel file that I'm hoping saved on my desktop. There we go. And I can actually open this Excel file and I can start to do some data processing on it. Or I can open it in, don't install. I know you're about to give me another warning, but I guess not today. Okay, cool. So I can actually take this data and I can just quickly drop it into Excel and actually do a fair amount of the analysis that I would normally do right here without having to get too crazy. I could also drop it into MATLAB and do the same thing, but this is really useful for when I'm trying to generate a report or if I'm trying to get some information about how my system is running. When you guys are working on your final project, we're going to ask that question. We're going to say, hey, the gripper that you're making, how is it behaving? What are the components of this and what does that look like? And so getting into the habit of this is super, super helpful because it gives you a lot of tools in the future to actually start modeling these parts. I will say this is not a cure-all, and I really think it's important to throw this out there because I think there's kind of this want for, hey, does this system do everything you need it to do? Kinda. But what matters is that if you don't know what it's not doing or what it's doing wrong, it can be really easy to have it mislead you. For example, I could hypothetically, and this is not something you need to do, I could edit a feature and I could say, all right, I actually need this to run at 1 million RPM. So something that I don't think I know of a bearing that could handle that kind of behavior. And because this is just a program, oh, nope, it's stopping me at 100,000. All right, we'll do 100,000. Please never run anything at 100,000. All right. And I could rerun and redo this entire program, and you can see that this entire system is just going nuts. I would actually have to severely increase the speed of my, or the resolution of my system in order to get this to work. But if I didn't know better, and I didn't know that, realistically speaking, running this motor at that speed would be impractical, I could hypothetically go to my boss and be like, hey, no, this is something that could happen. So knowing the limitations, the physical limitations of what you're working on is really important, which is why we have you guys do classes like statics and dynamics, where you can kind of get a feel for the back of the envelope calculations that makes it possible to determine if your simulation is reasonable or practical. Again, if you guys have any questions, feel free to flag us down. I'm going to try running this animation real fast just to see where it goes in a few seconds. If you will be more than happy to help. This is a nice, easy walkthrough before you jump into the next portion. And so what we're going to be asking you to do this week is, in addition to this system, we're going to be asking you to design a piece for a cityscape for a demonstration, and also for us to use as your mini project for this unit. So yeah, if you guys have any questions, feel free to flag me or Professor K down. We'd be happy to give you a hand. Talk to you guys in a few. Have a good one.